In this video, we're going to be talking about parent functions and transformations. So before we begin, we're going to have a quick review of everything or all the function types we know of. And here we have constant, linear, absolute value, and quadratic. And the graphs of all the parent functions, or the equation of the graphs of the parent function, and the graphs of the parent functions of each. And of course, the domain and ranges of each as well. So a transformation is something that changes the size, shape, position, or the orientation of a graph. A translation is a type of transformation that shifts the graph horizontally and or vertically, but it won't change the size, shape, or orientation. So since that is the easiest, we will be beginning with that one. So let's say there is a linear graph with the equation y equals x. Oh, sorry for the bad drawing, but what? Okay, y equals x. Pretend this is a straight line, and yeah, so this is y equals x, right? And then there's another line, and this line at is like the same, except it's here. Oh my, I really can't draw lines today, huh? But it's here. And this point is at 0, -4. This would be a transformation. This would just be a translation. No transformations yet. We're starting it simple. This would be a translation of 4 units down. So we know the graph of the red line is f of x equals x, right? So, we can tell that the blue is parallel, but it's not quite the same. And if we look at it, we see that the y-intercept is at 0, -4. And the original y-intercept is supposed to be at 0, 0. So this means that it was translated 4 units down. So we know this would be f of x minus 4. If that makes sense. This is also, in fact, the equation of this graph. So that's your translations. A quick example. I'll go through more examples after this. Next, we're going to be talking about a reflection. A reflection is just like actually, it is not like a translation. It is a transformation. It flips the graph over a line. This line is called the line of reflection. And the reflected point is the same distance from the line of reflection as the original, but on the opposite side of the line. So what does that mean? This means that there's going to be a line of reflection, and this line would have a point on one side that is the same distance to that line as another point on the other side. It's hard to learn just by hearing it, so I'm just gonna draw it out for you guys and show you what I mean. So let's say the line of reflection here is the x-axis, okay? So this line right here, the x-axis, that means every point on this side would be the same distance as the point on this side, which means it's gonna go like this, 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 and so on. So if we draw that out, we get another graph reflected. So as you can see, you see how the points are equal distance both sides as they are from the x-axis. This would be a reflection over the x-axis. You can kind of think of this as like, I guess, having something next to a mirror and how there's a reflection of that in the mirror as well. You can think of it like that. Or maybe you can think of having a book. let's say we had a book that we moved that we rotated 90 degrees, so it would be like you fold pages this way. Then if we fold the page, this graph would be directly on top of this graph. So that would be a reflection over the x-axis. And of course, it doesn't have to be just the x-axis. We can also reflect this over the y-axis. Now pretend this was never here. What would a reflection over the y-axis look like for this graph? I'll give you a bit of time to figure this out, so you can pause the video, think about this for a bit. That's right. So a reflection over the y-axis would be the exact same graph. And this is because if we had this line as our line of reflection, then it's already the same on both sides. So a reflection over the y-axis would do literally nothing to this graph. But keep in mind, this is only for the quadratic graph. Let's say we had a linear graph, a reflection over the y-axis would look something like this. Exact same thing, but reflected the other way. Now, let's talk about a vertical stretch and a vertical shrink. Vertical stretches and shrinks are slightly more complicated, but it's still pretty doable. So if we look at this, this is an absolute value function. So y equals absolute value of x, right? Now, let's say we want to reflect it so that y would equal 2 absolute value of x. Now, 2 absolute value of x would just make it so that the result would be double, right? Now, this just means when this is at 1, this would be at 2. Now, this would just kind of be more like this. So we can talk about doing this algebraically next video, but right now we're just kind of looking at all the graphs. Right now, you can imagine someone that kind of pulled on that graph, right? Let's say this whole thing was made out of like a really rubbery, like really stretchy material, and someone pulled that graph. You would imagine the graph from black, it would look like it would like you can imagine if the graph originally looked like the one in black, after they pull it, you can imagine it to look like the one in blue. That is what a vertical stretch does. You can think of this as stretching the graph vertically, right? That's pretty self-explanatory. And we also have vertical shrinks. Now that just kind of means the opposite. This would mean something like this would look something more like that. Obviously still the same absolute value function, except someone shrunk it vertically. That's like if someone went from the top and then pushed down, and it goes from the black one to the red one. The equation of that would be something like y equals 1/2 absolute value of x. Again, we'll go into much more detail about the algebra behind this, but right now we can just look at this, kind of get the idea of the graphs. And let's do a practice problem. Okay, so let's just move down a bit. Let's say we had this graph of a quadratic. What would a reflection, okay, I'll write this down. Reflection over the x-axis first a reflection over the x-axis, then a vertical shrink by 1/2. Then, so this is 3 steps further, two, and then third step, finally, 4 up. What would this graph look like? This is slightly more challenging. You can pause the video, have look at this problem for a bit. You don't have to have the exact like values for this graph, just a general idea. Okay, so if we look at this, the directions first say to reflect over the x-axis. So first, we're gonna have a reflection. So it's gonna be like, oh my, that was bad. It's gonna first be something like this over x-axis. Then it wants us to shrink it vertically by 1/2. So then next step, we're gonna have this same graph. We're gonna have this same exact graph, except it's gonna be slightly wider vertically. As you can imagine, someone pulling it horizontally or just pushing it down. So it's gonna look something more like that. That doesn't make that big of a difference. I want it to be more noticeable. Something more like this. Okay. That's a pretty big vertical stretch. This is definitely not by 1/2, but it's just the reference. So it doesn't really matter if it's accurate or not. And finally, it wants us to move the graph 4 units up. So we will move it about 4 units up. So this is at 4. Well, it's got to be wider, huh? So it's going to be 4 units up. So this would be what it would look like after all this. And again, next video, we're going to go into like the algebra and talk about also horizontal stretches and shrinks to make us understand this a lot more. And so we can also find the exact values. So instead of having this crazy of a vertical shrink, we'll have a much more accurate one so we can truly understand how how transformations would work.